A solution contains three volatile liquids, A, B, and C. The mole fractions are XA equals 0.2 and XB equal 0.5. No information about XC. We're given the vapor pressures of pure A, B, and C, respectively 100, 250 torr, where 1 torr is 1 millimeter mercury. Compute the vapor pressures of each component and the total vapor pressure above the solution. So if we drew a diagram to represent this, this is the liquid phase, this is the vapor phase here. We have A, B, and C in the liquid phase. All three are volatile, so we have a pressure of A, a pressure of B, and the pressure of C, and that's equal to the total pressure. Okay. So what we're given here is the mole fraction of A is 0.2. The mole fraction of B is 0.5, and nothing for the mole fraction of C. We'll get it in just a second. We're also given the vapor pressures of pure A, B, and C. So we create variables, P for pressure, subscript A for substance A, and for pure, the superscript 0. And we're going to assign the first value, since it's respectively 100 torr, or you could say millimeters of mercury. They're interchangeable. For the second pressure, the second component B, P for pressure, B for that substance, and 0 for pure, that's 200. And for the vapor pressure of pure C, that's going to be 50. So this time we want each of these vapor pressures. Okay. So you should know that I'll call it partial PB and PC can be computed. And we also know that the total pressure, PT, using Raoult's law, we could say XA PA0 plus XB PB0 plus XC PC0. Okay. Pressure, we also want these individual partial pressures. Each of these terms here signifies a partial pressure in the gas phase. So we could start plugging numbers in. We have the first two terms, XA and PA0. We have the next two terms, XB and PB0. We have PC0 but not XC. So we need to calculate XC. So remember that mole fractions always add up to 1, something I won't tell you on a test. So we can always get the last mole fraction by subtraction, knowing the other two. So we could plug some numbers in here. XA is 0.2, XB is 0.5, 0.7 plus XC equals 1, XC is 0.3. So you don't have to show this much work on a test. I mean, to be honest with you, you could pretty much skip all of this over here. I would want to see this equation here because it tells me that you conceptually understand how to set this problem up, that you have three components here, and you're writing a Raoult's law equation to compute total pressures, taking each component into account. So we're going to compute each of these terms individually. So XAPA0 multiplying 0.2 times 100. And we could do that in our heads, couldn't we? 0.2 times 100 would be 20. So that's the next term, XBPB0, would be 0.5 times 200. So 200 is 100. And then the third term here is 0.3. Times 5 is 15. Turns out to be 15.0. 20 plus 15 is 135.0 millimeters of mercury. So we've computed the pressures of each component in the gas phase. You could have done it here and just said this is PA, this is PB, and this is PC. This is really what you need to show on the test. Okay? You don't need to show all the definitions. I'm doing that to try to help you construct the problem. All three are volatile, means that all three of them get into the gas phase. I wouldn't have to tell you they're volatile liquids, because when I tell you that the pure vapor pressures are 100, 250, that means that they're all going into the gas phase. They're all volatile. Let's look at the next problem. So number 3, I have it on page 27. A binary solution contains two volatile components, A and B. Well, that's kind of redundant, isn't it? But sometimes I am redundant to explain the problem. If I say it's binary, that means there's two components. So I necessarily wouldn't need to say two. The total vapor pressure above the solution is 46 millimeters of mercury. The mole fraction of B is 0.6, and its vapor pressure is 30. Find the vapor pressure of A. So let's write down what we're given here. We have the total vapor pressure above the solution, so we'll construct a variable to represent total vapor. It should be pressure here. I'll be more exact on the test. So P for pressure, T for total, and we'll assign a value to it. The mole fraction of B is 0.6, so we create a variable for mole fraction of B, capital X for mole fraction, B subscript for species B, and we'll assign a value to it, given as 0.6. Its vapor pressure is 30, so that means B, so pressure of B is 30.0 millimeters mercury. Notice that I didn't say pure B here, I just said B. So that's going to make a difference in solving this problem. Our picture would be liquid, vapor. We have A and B, and we have A and B in the vapor. It wants us just to find the vapor pressure of A. Okay. So we could write out Raoult's law, but our total vapor pressure above the solution is just PA plus PB. And that value is given as 46. So in this particular case, we didn't even need to use Raoult's law. We didn't need to use the x's. So is 46 minus 30, 16.0 millimeters mercury. So this one's pretty simple. And the main idea here is that I didn't give you pure vapor pressure. I gave you the partial pressure of A above the pressure of B above the. Be distinguished between the two. So I just wonder, let's say if I go up here and I show ribbon and I do ink replay, let's see what will happen here. I suppose this would give me a way of dubbing in the audio after I actually work the problem. What I've noticed here is that sometimes at the top and bottom it doesn't appear in the videos. I need to be careful about going down too far or going up too far. Next problem. At 25 Celsius, a solution contains, let me just bring this down a little bit, 1.75 moles of methanol and 3.28 moles of ethanol. The vapor pressure of pure methanol is 143 millimeters of mercury, and that of pure ethanol is 96. Find the total vapor pressure above the solution. Okay, so total vapor pressure calculated from pure, vapor pressures, we can use Raoult's law. So let's assign some variables and numbers to what's given in the problem. So this is really the first thing here. 1.75 moles of methanol. We use N for moles. I'll use M for methanol. Second thing given is moles of ethanol, N for moles, E for ethanol. Vapor pressure of pure methanol, P for vapor pressure, M for methanol, 0 for pure. And the last thing, vapor pressure of pure ethanol, P for pressure, E for ethanol, 0 for pure, 96.0. Right, so what if I did this? I could say total vapor pressure above the solution is mole fraction of methanol times vapor pressure of pure methanol plus mole fraction of ethanol times vapor pressure of pure ethanol. And I started plugging in numbers. Is this correct or incorrect? This is incorrect, right? And the reason I've shown this mistake is because I've seen it on examinations, and I don't want you to do the same thing. So these are mole fractions. But in this problem, I wasn't given mole fractions. We were given moles. So we're going to have to compute mole fraction from the given moles. Okay? So we can say let X M be the mole fraction of methanol. We're given the molecular formulas, but I don't think we really need to use them. Okay? If you're interested in the structures, the methanol, the CH3OH, looks like this. It's a carbon with 3 hydrogens on it. It's called wood alcohol. You can buy it in the hardware store or in a drugstore. It's very poisonous though. And the second one is ethanol, CH3, CH2OH. And that structure, you do the 2 carbons first. We'll put the 3 H's. Every carbon is 4 bonds, so 3 H's there. 2 H's here, and then an O and an H. These are both polar covalent liquids, so they're going to be miscible with each other. But you really didn't need the structures. We want to focus on the mole fraction of methanol. So that's going to be the number of moles of methanol over the total number of moles of the 2 components in solution. You wouldn't need to write that equation. I'm doing it to try and explain it to you. And then we would substitute in the given moles that we have, 1.75 for methanol, 1.75 again, and 3.28. So that means this number is 0.348. So I'll erase this here. We could compute the mole fraction of the ethanol by doing this. But remember, it's easier to get it through subtraction. You can always get the last mole fraction by subtraction. Since mole fractions add to 1, xm plus xe is 1. xe then is 1 minus xm. 1 minus 0.348 is 0.652. Okay? So that's probably a little bit faster. A little bit faster to compute that last mole fraction by subtraction instead of going through the more tedious fractional calculation. So we can now expand our equation with the numbers that we have. We can have 0.348 times plus 0.652 times that. So 49.8 plus 62.6 is, don't forget the unit. We need 1 decimal point in our answer because using sig fig rules for addition and subtraction, you keep in the final answer the same number of decimal places that you have in each of the preceding figures. So the total number of sig figs can change when you do addition and subtraction. We're going from 3 to 4 sig figs because we're conserving decimal places. Do you have a question? So the main difference between this problem and some of the others is that this time we weren't given mole fraction, we were given moles. So we had to compute mole fraction from the moles. So this is a variation of the previous problem. In number 5, we still have a new variation of the previous problem. The vapor pressure of pure cyclohexane is 77.5 millimeters of mercury, while that of pure hexane is 124. Given a solution containing 40 grams each, compute the solution vapor pressure. So we have 2 liquids, okay? And they're both volatile because we're given vapor pressures for each of those. So we can use this equation, P total, well, let me write it here. P total equals mole fraction of the first component, I'll call it CH for cyclohexane, times the pure vapor pressure of cyclohexane, plus mole fraction of the second component, hexane, times its pure vapor pressure. We can use this equation here. As far as structures go, cyclohexane is a ring. It's a hexagon. Hex means 6. It's a ring that contains 6 carbon atoms in the geometrical shape, the polygon called a hexagon. And chemists just draw this structure here. Each carbon is at the vertex here. And since each carbon has 4 bonds, that means there's 2 hydrogens on each of those vertices, which aren't shown in the structure. They're assumed to be there. So this is cyclohexane. I'm calling it CH. And its formula is C6H12. The second compound is hexane. That means it's a straight chain. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Chemists often draw this zigzag structure for straight chain compounds. Each vertex, again, is a carbon atom, and the hydrogens are assumed to be on each vertex there. There's 3 H's here, 2 H's there. not shown. But the formula then is C6H14. So we're given the vapor pressures of pure cyclohexane. Vapor pressure of pure hexane is 124. Vapor pressure of pure cyclohexane is 77.5 millimeters of mercury. And we'll create a second variable. Pure vapor pressure of hexane is 124. So we know those two parameters right there. But we don't know the mole fractions because we're not given mole fractions. We're not given moles, we're given mass instead. So in this particular problem, we have to convert mass to moles. And then mole, some of our symbols, we often use lowercase m for mass, N for moles, and capital X for mole fraction. To convert mass to moles, we divide by molar mass, capital M. So let's do that. Let's compute the number of moles of cyclohexane and hexane. To do that, we need the molar mass. So molar mass of cyclohexane. I gave you the chemical formula here. There's 6 carbons, each with an atomic weight of 12.01. I'll give you a periodic table with the test, one that I have in the course pack, so you can look up the atomic weight. The second atom in this formula is hydrogen, and there's 12 of those. So we add 12 hydrogens times the atomic weight of hydrogen, which is 1.01. 6 times 12 is 72. This should give us 72.06. And this should give us 12.12. And then if we add it up, we get 84.18 grams per mole. You should know how to do that. That's important. All right, so then the other molar mass that we need is for the hexane, molar mass of hexane. We look at its given formula, which is C6H14. So 6 times 12.01 plus, but we realize the only difference in molar mass is going to be the mass of 2 hydrogens. We're going from H12 to H14. 2 hydrogens have a mass of 2.02, so I could actually add 2.02 to this instead of doing this long drawn-out calculation. And we're going to get 86.20 grams per mole for the molar mass of hexane. It might be easier for you to just multiply it out. All right, so then next we're going to compute the number of moles, N, of cyclohexane. You can use dimensional analysis or you can use the memorized algorithm. Moles is mass over molar mass. Okay, so that's going to be 40 grams, 84.18. The grams cancel, the moles go into the numerator. Or if you want to use dimensional analysis, you could have set it up this way. 40.0 grams. If you like, you can put that over 1 times 1 mole per 84.18 grams. That's going to give us 40 divided by 84.18, 0.475. We can do similar calculations for the number of moles of hexane. The mass, again, is 40 grams. Its molar mass is 86.2, or we could have said 40.0 grams over 1 times 1 mole over 86.2 grams, 0.464. Suppose I should tack units on there. Next, we can compute mole fractions. The mole fraction of cyclohexane is going to be the number of moles of cyclohexane over the total number of moles of cyclohexane plus moles of hexane. Plugging in numbers, that's going to be 0.475 over, that sum gives us 0.939. We can do a similar calculation for the mole fraction of hexane, but it's easier to get it from subtraction. So we'll do that. Mole fraction of hexane is going to be 1 minus the mole fraction of cyclohexane, 0.494. All right, so we can take those numbers and plug them into our master equation. Cyclohexane 0.506 times the vapor pressure of pure cyclohexane 77.5 plus mole fraction of hexane 0.494 times its vapor pressure, 124.0. 0.506 times 77.5, 39.22, 61.26. Add them up, get 100.5. It might be too long to put on an examination, but it should help you with your thinking about these problems, about the concepts. We'll be covering a lot more material, so there isn't any way that I can put every type of problem that we've done in class on a test. I have to be judicious on what I select so that you have enough time to do it. Okay? So I'll let you do problem number 6 on your own. The answer is already up there, and 7 as well. Those answers should be up there on Canvas. And our next topic is boiling point. So we have two terms, boiling point and normal boiling point. We have fixed the prefix normal when we're at sea level, at which the atmospheric pressure is 1 atmosphere or 760 millimeters of mercury. In other words, the pressure of an atmosphere would push up mercury to a level of 760 millimeters. We're close to sea level here. Okay? We're not that far above it. So to explain boiling point, pretend that we have a beaker here. It really doesn't quite look like a beaker because it doesn't have that little lip on it, you know what I mean? It's supposed to have that lip, but I didn't see that in the PowerPoint, so I just made a cylinder. And let's pretend we have some water in here and we throw it on a hot plate and we heat it up. First thing we're going to see is air bubbles. There'll be little bubbles inside the liquid. Those are air bubbles, air coming out of the water. They're going to evaporate right out. As we continue heating, if we look closely, the liquid volume would expand a bit. Finally, when we get to the boiling point of water, 100 degrees, there'll be flash evaporation of pockets of water inside the liquid. The flash evaporation creates little steam bubbles, not water molecules. Those steam bubbles, being less dense than the liquid water, are going to rise out and come out of the liquid water, giving an upward pressure coming out of the water, an upward pressure of steam coming out of the liquid. When that upward pressure is equal to the atmospheric pressure, we're at sea level, so it's 1 atmosphere, we have boiling. If we enclose this, made it a closed system, we kept the pressure 1 atmosphere, the temperature would stay constant at 100 degrees, and we would have an equilibrium between evaporation and condensation. Okay? If we have an open container, the temperature is still going to stay at 100 degrees until almost everything evaporates out. But at the boiling point, the temperature is constant until everything boils away. So we could actually represent boiling by this symbolic equation. It's not a chemical change, it's a physical change. It's not a chemical change because there's no change in the water. When people have given students tests on what boiling is, some students think that the water actually breaks down into hydrogen and oxygen. It doesn't. Okay? It stays the same substance before and after the change. The temperature is constant. The only thing that changes is the phase, liquid to again. At the boiling point, the temperature is constant. Now, if we went to Denver, where I was last week at a chemical conference, y'all know it's a mile high, because at a mile in altitude, the air is less dense. The atmospheric pressure is less. In fact, the atmospheric pressure is 0.82 atmosphere. So the water doesn't need to get to as high a temperature to generate 0.82 atmospheric pressure coming out of the liquid. So the boiling point is lower at 95. So boiling point depends on altitude. The word normal means we're at sea level. We'll assume in all of our problems that we're at sea level. Boiling point also depends on intermolecular forces. As you know, water molecules have this London dispersion force, but more importantly, the hydrogen bond between them. So we can show these intermolecular forces as dotted lines between two adjacent particles, which here represent water molecules. When these intermolecular forces, like the hydrogen bond, make a strong bond or binding between the two molecules here, it takes extra energy to actually boil the substance because these hydrogen bonds have to be broken. Now, the hydrogen bond is not a formal chemical bond. It's a dipole-dipole, of course. But because water molecules have this strong hydrogen bond between them, the strong dipole-dipole, of course, the boiling point of water is quite high at 100 degrees. If we took a similar compound, H2S, where sulfur is under oxygen in the periodic chart, H2S is almost a nonpolar molecule. The electronegativity of hydrogen is 2.1, that of sulfur is 2.2. The difference is only 0.1. That's basically a nonpolar molecule. It doesn't have even dipole-dipole forces. It only has Lindh dispersion force. If you look up the boiling point of hydrogen sulfide, which is a poisonous gas, smells like rotten eggs, the boiling point is going to be around 0 degrees Celsius. So the difference in boiling points between two compounds that are similar in shape and structure, they both have central atoms from the same group, group 6A, the oxygen group. The water is 100 degrees. Hydrogen sulfide is around 0. That's because of the hydrogen bond. It takes extra energy. In this section here, we're going to cover boiling point elevation. So the elevation here doesn't refer to altitude. It refers to an increase in boiling point of a solution versus a pure solvent. So when we make a solution by adding a solute to a solvent, it turns out that the boiling point of the solution is higher than that of the pure solvent. For example, we all know that water boils at 100 degrees Celsius. But if we add any solute to the water, the solute could be sodium chloride in cooking, could be sugar water, sucrose. Anyway, if we make a solution by adding something to that water, the boiling point of that solution is going to be higher than that of the pure solvent water by some amount. It could be a small amount, like only 1 degree. Or if you use antifreeze and you have a high percentage of antifreeze in the water, the boiling point could be a lot higher. Okay? The more solute particles that are dissolved in the solvent, the larger is the increase in boiling point. So we talked about colligative properties as properties depending on the number of particles of solute in the solvent. So the higher the number of solute particles, the higher is the boiling point elevation. So I'll illustrate that. Add this little picture. Let's say that we have a solvent. Let's make it water so that we know the boiling point of water, T sub B, is going to be exactly 100 degrees. We could affix as many zeros as we want to this. It's an exact number. We're setting the boiling point of water to be 100 exactly. Now let's make a solution by adding some sodium chloride to it. Okay, so now we have a sodium chloride water solution. The new boiling point is going to be higher than the boiling point of the water by some amount, delta T. We can call that delta T the boiling point elevation. So the new boiling point, T in boiling point, plus the boiling point elevation, and maybe we measure 101 degrees Celsius. Well, Van Taw figured out how to compute this delta T so that we didn't need to go into the laboratory and actually measure the boiling point of every solution out there. We can predict it in advance. So the equation that allows us to compute the boiling point elevation, I call it here increase in boiling point. We can say it's the boiling point elevation. Delta T, change in boiling point. We can compute it by multiplying three factors together, I, Kb, and Cm. I is an integer. It starts at 1 and goes up. Probably you're not going to see it go above 3. Kb is a constant that depends on the solvent. If Kb is water, the values, I think, is 0.52. Check it out. So Kb is a constant. I would give it to you. It depends on the solvent. If we take water as our solvent, as we usually will, that number is going to be 0.52. And Cm is the concentration of the solution. Solids in the solvent, it's a molal concentration. Some books will just write lowercase m because that signifies molal, which means number of moles of solute in number of kilograms of solvent. I use Cm, C for concentration, lowercase m for molal to help you remember that. Let's look at I. I is greater than 1 if we have an ionic. So what's an ionic compound? It's a salt. It contains a metal and a nonmetal. It's an ionic compound because it's made of ions. So to figure out whether I've given you an ionic compound or not, look at the formula. Sodium chloride. Sodium is on the left side of the periodic chart. It's a metal. Chloride is on the right side. It's nonmetal. Yes, this is ionic. Calcium chloride is in group 2A. It's a metal, obviously. Chloride is a nonmetal. And then the third one here, CH3OH, it's a carbon compound. There's no metal and nonmetal here. I suppose you could say carbon, H, and O are nonmetals, but there's no metal. So if it's a carbon compound, then I is automatically equal to 1. Assume there's no ionization. Okay? So that's why for this last case, just write I is equal to 1. You don't need to justify your answer. But if you have an ionic compound, you're going to need to justify your value for I by writing its ionization equation in water, assuming I give you water as a solvent, which I will. So when you put sodium chloride in water, it dissociates into its two-component ion, sodium and chloride ion. There's 2 particles on the right side, so I is 2. You can figure that out by seeing that there's 2 particles, 2 ions in the original compound as well. For the next one, calcium chloride, it gives 1 calcium and 2 chlorides, 3 particles overall, so I is equal to 3. CaCl2 is not a chlorine molecule bound to a calcium. It's a ionic compound, meaning that these chlorides are actually ions, -1 charge. So a picture model would be positive 2 calcium and 2 negative chlorides. Everything is bound together by the electrostatic force of attraction, the ionic bond, okay? So metal and nonmetal is automatically ionic. You can count up the number of particles to generate your value for I. But on a test, I would make you support your value by writing an ionization equation correctly. So that's how we figure out I. It's an integer. If it's a carbon compound, I is automatically 1. If it's ionic, then you can figure it out by writing the dissociation equation. Kb is a constant, probably given with the problem. Depends on the solvent only. And Cm is the mole concentration. You might be given its value, or you may need to use this formula to compute it out. As far as units go, we know that since we're measuring temperatures in the laboratory, we're going to use the Celsius scale. So delta T is going to be degrees Celsius. I has no units, it's just a number, an exact number, infinite number of decimal places. We know the units for mole concentration, moles per kilogram. So that forces Kb to have these units here. To get degrees Celsius in our answer, we have to have degrees Celsius in the numerator here, and we have to be able to cancel out moles per kilogram, so kilograms there and moles there. Okay? This is the boiling point elevation. Solvent and add to it the delta T factor. This gives us another way of computing delta T. Usually you won't be doing it this way, but if we had the boiling point of the solution and we subtracted the boiling point of the solvent, that's the other way of getting delta T. In most cases, you'll be computing delta T using I, K, B, C, M, and adding that to the boiling point of the pure solvent, which for water is exactly 100 degrees. So in your problems, if I give you water, I'm not going to give you the boiling point of water. That's a fact that you should know. And as I mentioned before, Kb for water, you don't need to memorize it, is this number here. So the next topic is freezing point depression. So to remember which one goes up and which one goes down, just think of antifreeze in your car radiator. We add antifreeze to water to make a solution that prevents the radiator from freezing up, becoming a block of ice on a cold winter day, and also prevents it from overheating on a hot day. Okay, so the antifreeze makes a solution that raises the boiling point and lowers the freezing point. So it's easy to remember which one is which. So in freezing point depression, when we add any solid to a solvent, we're going to decrease the freezing point of the solution compared to that of the pure solvent. So this one is going down. So for example, if water is our solvent, we all know that it freezes at exactly 0 degrees Celsius. And adding any solid to the water is going to shift the freezing point to a lower value, say maybe minus 1 degree Celsius, or if we use antifreeze, we might get to minus 80 degrees Celsius. Again, the more solid particles, the higher the concentration of the solids, the more solid particles dissolved in the solvent, the larger is the decrease in the freezing point. So this time we start with water, say as a solvent, whose freezing point you should know is 0. If we add a solid to the solvent to generate a solution, say salt, that salt water solution is going to have a freezing point below 0. It's going to be a negative number. So that would be the freezing point of the solvent. Here it's water at 0, and the freezing point of the solution is going to be the freezing point of the solvent minus that change in freezing point. That's something you should know. I won't tell you that, just like I won't give you this equation on a test. This is a conceptual thing that you should understand. All right, so we can calculate delta T for freezing point depression in a similar manner as to boiling point elevation. We multiply 3 factors together. I is the same variable we had before for a carbon compound. I is always equal to 1 for an ionic compound. I is an integer larger than 1, usually 2 or 3. Again, Cm is the mole concentration of the solids in the solvent. Again, the units cancel out just as before. Okay, so then, summary of the equations. Our solution freezing point is going to be that of the pure solvent minus delta T. Why do we have boiling point elevation and freezing point depression? To try and explain this on a molecular level, using water as our solvent. We all know that water molecules are attracted to each other through this hydrogen bond, which really is not a chemical bond, but it bonds the two molecules together through a dipole-dipole attractive force. If we add a solid to the water, say sodium chloride, it's going to dissociate into ions, and those ions are going to get between the water molecules. When we have a sodium ion between two water molecules, there's going to be a strong ion to dipole attractive force between the positive sodium and the negative oxygen pole of the water. It's actually a stronger electrostatic interaction than from two dipoles, from two water molecules. Likewise, if a chloride gets between the hydrogen pole of a water molecule and the oxygen end, or between two hydrogen ends, is going to create a strong attractive force here, negative ion to positive dipole. In order for water to freeze, it has to get into a crystal lattice where the entire ice lattice is held together only by hydrogen bonds. So if you had a block of ice, okay, that would mean that all of the individual atoms are held together in this crystal lattice in their fixed position by hydrogen bonds. So for water to freeze, it needs to get into that hydrogen bonded structure. It needs to somehow get closer together away from the sodium and chloride ions. To do that, it has to go to a lower temperature. As it gets to a lower temperature, the water molecules are able to get together. In fact, you would see a separation between the solids and the solvent. I once tried it with some sugar Coke. I put the sugar Coke liter bottle into the fridge for like a week, and when I looked at it later on, they were clear, and it's probably the other way, clear, and then colored, maybe brown, dark brown. What happens at the water molecules as they actually froze out into their hydrogen bonded structure, that was clear, like clear water, and then the sugar and the syrup and the dark coloring in there gave another layer in there that separated out. For boiling point, when you have like a sodium ion forming a strong electrostatic attraction to a dipole, the oxygen and polar end of the water molecule, that's a strong bond. You have to put extra energy in to break that, and so that extra energy causes the boiling point to rise. I'm not going to ask you to explain this on a test. The next and last collective property is osmotic pressure. It's the pressure But instead of using P for pressure, we're going to use the Greek letter pi so that we don't confuse it with vapor pressure. Okay. So to explain osmotic pressure, I remember when I once taught high school biology, I set up an apparatus like this in the classroom. I had a large beaker that contained pure water. I bought from some biological supply store a semi-permeable membrane. I think it was an animal intestine. I had that here. And inside that, I put a tube like a burette, tied it in there at the top there. And inside this chamber, I have a sugar water solution or salt water solution. Now, semi-permeable membrane works so that only water molecules can move through it. The pores are so tiny that water molecules can move through it, but anything else can't. So, since we have a concentrated solution, say sugar water inside this chamber here and pure water here, two solutions want to come to the same concentration. So that means that the solvent is going to start moving through that semi-permeable membrane, increasing the pressure inside this, causing the water to move up to the tube. So that's what we mean by osmotic pressure. It's the pressure of the solvent moving into the semi-permeable membrane. You can actually calculate it out. We can calculate it out by using a formula that's derived analogous to the ideal gas law. So ideal gas law is PV equals nRT. P is pressure, V is volume, N is number of moles, R is a constant, and T is temperature. If we take this equation, we divide both sides by V, we would get P is N over V times R times T. N over V is number of moles in volume of solution, liters of solution, okay? Moles per liter, which is molarity, and we use the simple capital M for molarity. So we're going to substitute for N over V capital M to signify we're computing osmotic pressure. And then to correct for any ionization, we'll throw in the factor I. So this is the osmotic pressure equation. I would give it to you on a test, but you have to know how to use it. Looking at it more closely, the osmotic pressure is going to be in atmosphere. I has no units. There's an exact number, infinite number of decimal places. M is molarity in moles per liter. R is a gas constant, and T is temperature in Kelvin. R, the gas constant, has a value of 0.08206, and its units are liters, atmospheres, moles per Kelvin. So I would give it to you on a test. You're going to see this on the test somewhere. It could be on the equation sheet, or it could be in the problem that I give. Some students have trouble remembering what units to use. Some students will use deltas. They'll use degrees Celsius instead of Kelvin for the temperature. To help you understand what units you need to use for each of these parameters or variables in this equation, all that you really need to do is look at the units that I've given you for R on the test. If you look at the units for R, it's per Kelvin, so that forces this temperature to be in Kelvin. So T in Kelvin is equal to degrees Celsius plus 273. That's a fact you should know. We have atmospheres here, so the pressure that you compute must be in atmospheres. I has no units. What we have left is liters over moles. To cancel that out, capital M must be moles per liter. Must be molar concentration. So if you don't remember that capital M means molar concentration in moles per liter, you can look at the value, the units for R that I've given you. Here I've shown how they actually cancel out. Everything cancels out except for atmosphere. So we're computing osmotic pressure in atmospheres. So here are some problems. Right, let's work through a couple of these. The Van 't Hoff equation is usually written this way. This would be like for freezing point depression, delta T is IKFCM, where I is the total number of particles in solution. Some authors just write the equation this way. They'll just say KF times CM, where that's the total, if I can write right, total molal of all I in solution. That total concentration would just be I times CM. Avoid the I because they'll say we'll let the molal concentration be the total concentration of all the particles in solution, ICM. So let's compute the product of ICM for these cases here. 0.1 molal sodium chloride, 0.1 molal magnesium chloride, and 2 molal methanol. So to do that, we need the value for I. So we remember that in water, NaCl gives us Na plus Cl negative. I is equal to 2. So then C total is 2 times 0.1, 0.20 molal. That's the total concentration of all the particles in solution in molal units. For the second case here, magnesium fluoride. This is not a fluorine molecule bound to magnesium. It's 2 fluoride ions. So we get Mg2 plus. I is equal to 3. Actually, you can get it right there. Total concentration is 3 times 1 molal. And then for the last case, we have a carbon compound, so I is equal to 1. There's no ionization. So the total concentration of all the particles in solution is the same as the given molal concentration. The reason that I've gone through this particular problem here is not because I'm going to probably ask you to do this on a test. It's because we're going to use it to solve the next problem here. In the next problem, we want to arrange these substances in order of decreasing freezing point. So we're given sodium chloride, ammonia, magnesium chloride, and another ammonia solution at a lower concentration. We want to arrange these in order of decreasing freezing point. So our concept here is the more solute particles we have, the lower is the freezing point of the solution. Or in other words, the higher the molal concentration, the lower the freezing point of the solution. That's the concept. Mathematically, we know that the freezing point of the solution is equal to the freezing point of the pure solvent, here it's going to be water, minus that freezing point depression delta T. I think in your book I have this in aqueous solution. You would assume it was, check it out here. Yeah, water. So our water freezing point is this, and we have IKFCm here. So what I said in words really is maybe shown even more clearly by this equation. The higher the value of this second term, because we subtract it from 0, the lower is the freezing point. So we could have arranged it this way. Kf is a constant. So we'll put it up front. And we have I times Cm. Well, isn't that the same as total concentration of all the species in solution? So to really figure this out, we need the product of I Cm. The higher this second term, the lower is the freezing point. So let's make a little table here. Let's say we have sodium chloride, that's our particle. This will be Cm, and this will be I, and a third column for I times Cm. So for NaCl, we're given this as 0.3. We know that I is 2, so I times Cm is 0.6. The next one is ammonia. It's not a metal, non-metal, so we assume no ionization. Its concentration is 0.75. I is equal to 1. I times Cm is 0.75. For the third one, magnesium chloride, it's ionic. 0.2 is the concentration. I must be 3. So I times Cm is 0.75. And for the last case, ammonia again, but at a lower concentration. I is 1, so we get this. So then the larger value here, the biggest value here has the lowest freezing point. We want to arrange them in order of decreasing freezing point. Now, to be honest with you, if you have them in the correct order, I would give you full credit, but you just have to make sure you tell me which one is high and which one is low. You can write the word high or low on numbers. You could use greater than or less than symbols if you like. We're trying to go from left to right, though, and decreasing freezing point. Okay, so decrease, this means the highest concentration, and this is the lowest. So the highest freezing point is going to have the lowest concentration. So the lowest concentration that we have here is this one here. So ammonia has a higher freezing point than the NaCl at the concentration is given, and it has a higher freezing point than the ammonia, which is the same as the magnesium chloride because they're both 0.75. This is lowest freezing point, highest. Like I said, you could say high and low, fix them to the numbers, or you can use greater than signs. So these last two had the same value of I times Cm, so they should have the same freezing points. But it turns out that the freezing point of the magnesium chloride is going to be actually a little bit higher because in solution, to a very small extent, some of the chloride ions can tie up with the magnesium ion to form what's called an ion pair. So I've actually worked where I had to measure these in solution, okay, and correct for them in calculation. They do exist to a very small extent, which would be important for precise research calculation that you don't need to know. We'll stop right here. I think I don't want to move too far ahead here. We'll go from here. Let me know if you have